All right, okay. So the first method, okay, I think that the first method is based on the production of vapor by boiling the liquid to be separated and then condensing the vapor with allowing and a liquid to return to the still. Okay, so I think that the first method, I think you are familiar if you go to the lab and you can see how actually the distilled water is made. So the concept of distilled water production is actually using the concept of the simple distillation column, whereby the water, okay, will supply by the heat and it will change into the vapor, and then it will go to the condenser, and then the vapor will change into the liquid, and then we'll take out from the system. Okay, so maksudnya dekat situ there is no return of the liquid from the condenser back to the column. Okay, so that's the first method. However, usually in industry, all right, okay, in the industry, okay, what we're gonna refer, or what we always use is what we call as a continuous distillation, or in other words, we call it as a rectification. Okay, so in this type of distillation column, okay, we will install usually the condenser, okay, at the top of the column, and reboiler at the bottom, so that there is a returning liquid back to the column. Okay, so this is the official statement, okay, based on the written part of the condensate to the still until such condition that is returning liquid is brought back into the vapor inside the distillation column. So for today, okay, so for our syllabus, okay, so we're gonna focus on this continuous rectification column. All right, so if you look into our lesson plan, okay, so by right for today, we should cover on this, what happened? Continuous distillation. Sorry. Okay, we should cover on the continuous distillation. Okay, it start with process descriptions, mean why that you need to know to understand about how the sketch of the distillation look like. Okay, the distillation column will look like, where is the location of the condenser, where is the location of the reboiler, okay, what we call the stages for the upper part, okay. And then the most important things in this continuous distillation is that we want to calculate the number of theoretical stages needed, which is the number of n. Right, and after that we need to calculate, okay, first you need to understand, okay, what is the reflux, what is the meaning of the reflux, and what is the meaning of the minimum reflux ratio and the total reflux ratio. Okay, so these two things, okay, for the number of stages and this reflux ratio, okay, there is two approach of method. And then for the first for today, okay, we will cover on McCap and Thiel method. Okay, so maybe on the second class or maybe on the next week, we'll start to cover on the Lewis-Sorel method. But this objective, okay, either one, okay, whether you use the first method or second method, okay, the objective is that we want to calculate for the number of the stages. All right, so later on, we will cover on the 3 deficiency, maybe next week. All right, so now go back to the topic 1, part 2, okay. So this is a very brief description of the continuous distillation. Okay, so if you look out into your book, okay, page 706, because this is the second time actually that you use the reference books of Dean Copley, so I expect that each of you, at least if you doesn't have the hard copy, you should have the soft copy by now. Okay, so the detail on the explanation about the description of process flow is stated inside the book, but by right, okay, this is the sketch that at least you need to know. Okay, so this is the distillation column, so it's usually coming in a long cylinder. Okay, the shape is in a cylinder. All right, so you have a feed coming from the in the middle. Okay, so let's say that determining feed from here. So you know that the concept is that it apply the heat. Okay, we supply the heat in such a way that the component, okay, the multi-component in feed which have a different boiling point will start to separate accordingly. Okay, so by right, the component, let's say component A, okay, with less boiling point, okay, will change into the vapor and go to the top of the column. So you can see that coming out from the top of the column is in vapor phase. Okay, it's in vapor phase. So for the case of this continuous distillation, okay, usually we will have this condenser. All right, so condenser is installed at the top of the column so that this vapor will change into the liquid. All right. And from this liquid, okay, from this liquid, not all the liquid is taken out from the condenser. Okay, there is some portion that will go back to the column, and just some portion will we take out as a product, which we refer as a overhead product or distillate. So after this, whenever you have the word distillate, okay, you know that this is actually a distillate, sorry, the liquid product that coming out from the top of the column after they have gone through from the condenser. Means that the original phase is actually in vapor, then go to the condenser, okay, then the phase is changing from vapor to liquid, okay. So some part of the liquid will take out as a product and some part will be recycled back to the column. So this recycled part we refer as a reflux. Okay, so usually we label as a L. Alright, so D here is the unit, let's say in kilogram mole per second. So L is a kilogram mole per second. Okay, this is the reflux. Alright, so that's for the upper part. Okay, so the what we call bahagian atas daripada feed, okay, until the top, okay, we refer as a enriching section. Okay, the section of from the top until the feed, okay, we call it as an enriching system. So you know that this enriching system, okay, will cover all those things which is contains of this condenser and the reflux. All right. Now for the lower part of the column, okay, we label it as a stripping section. Okay, stripping section. So you know that the component with high boiling point, okay, will go to the bottom part, okay, to the bottom part of the column in liquid. So you can see from the at the upper part vapor, so the liquid coming from the bottom, and right here, okay, this liquid will go into the reboiler. Okay, so you need to know the basis. The reboiler is usually installed at the bottom part of the column so that this liquid will be reboiled again. All right, reboiled again, and all the remaining, okay, if there is a component of A, okay, which yang terlepas masuk dekat dalam ni, okay, means that a component with a lower boiling point will be vapor again and go back to the column. So means here inside the boiler, okay, only a component with the high BP will maintain, right? And then this product will come out also as a liquid form and is known as a bottom liquid product. And usually the label will label as a W. Alright, so for a basis of distillation column, okay, so usually the molar flow rate, okay, the entering feed will label as a capital F, okay, in kilogram mole per second. So we have the D as a product coming out from the distillate atas, okay, also in a liquid form. And we also have a product, okay, in liquid form coming at the bottom part, and we label it as a W. This is also a in kilogram mole per second. Okay, so this is the system that we discussed for today. Okay, we call it as a continuous distillation or rectification, whereby you know that this system usually consists of these two things, okay, condenser and reboiler. All right, so that's a brief explanation about this. Okay, so if you read here, okay, the feed liquid mixture of A and B enters the column and flow down to a tray. Okay, vapor enters the tray and flow upwards. The concentration of more volatile components, okay, lower boiling point is being increased in vapor. Okay, so the components, as I said before, the component with less lower boiling point will change to the vapor and become a vapor-rich condition and go to the top. Okay, and the final vapor, okay, is condensed and only portion of the liquid product is removed. Okay, and remaining liquid is what we refer as a reflux. Okay, and the liquid leaving the bottom tray enters a reboiler and partially vaporized. So means here, if there is a component with a lower boiling point, will vaporize again and back to the column. All right, so I think this is I hope that you understand, okay, so far about the system of the continuous distillation column. Okay, so usually, okay, so for today, okay, we only cover about a binary mixture. Okay, when I mentioned binary mixture, I know, okay, you already know that we only have two components, which is components A and B. Okay, liquid mixture of A and B. We are talking about a simple system first. Okay, just to get ourselves familiar with the distillation column. Okay, right now, usually, okay, in the determination of number of plates, all right, so usually in the system, okay, we actually when we want to design the distillation column, okay, we actually make a target. For example, that you know what is the molar flow rate, the feed coming in, and you want to have a certain target. For example, that 0.45 of A coming in into the column, and you want that the molecule of A is go to the top as a 0.9 mole A. Okay, so we want to know, okay, kalau kita nak 0.9 mole of fraction of A go to the top and 0.1 going to the bottom, okay, what is the number of stages required? Okay, how tall your column might need, okay, to achieve your desired condition. All right, so for the case, okay, to calculate the number of plates here, the main assumption, accumula overflow through the tower between the feed inlet and the top tray, and the accumula overflow, okay, between the feed inlet, okay, and the top tray, and the feed inlet and the bottom tray. Okay, so kita assume that there's accumula pergi ke atas dan pergi ke bawah. So usually, okay, this is the label, okay. If you see here, okay, here is the tray N. All right, so whenever the whenever the vapor, okay, vapor flow coming from the bottom of the N, we label as a Vn plus 1, and the mole fraction is Yn plus 1, and this one is Vn and Yn. So you know that the Vn is actually referred to the molar flow rate of vapor. Okay, so it doesn't matter if the label is Vn or Vn plus 1 or Vn minus 1. Okay, so you know it's actually referred to the molar flow rate of vapor. Okay, molar flow rate of vapor in kilogram mole per second. So when you have this label, small y, and so you know that it's referred to the mole fraction. Okay, so if it is Ya, means that is a mole fraction of A in vapor phase. All right. Same thing goes to the, so you know that the upward arrow refer to the movement of the vapor from bottom to the top. And you can see that the pointing downward arrow here, it is referred to the movement of the liquid phase. Okay, so we label as a Ln, Sn, all right. So, if you look out here, okay, the upper part of the tower above the feed entry is called enriching system. Okay, saya dah beritahu tadi. Sorry. here, okay, this is the example of the total material balance. So after this, okay, next to slide, when we do the material balance, okay, you know that the material balance is conducted at this boundary, okay, so you know that Vn plus 1 plus Ln minus 1 is equal to Vn plus Ln, okay, so the total material balance is performed, okay, on this boundary. Okay, so when you do the mass balance of the component A, okay, you just multiply it with the mole fraction of the A respectively. All right, so usually the unit is in mole per hour, kilogram per hour. Okay, so word V, capital V will always refer to vapor. Capital L will always refer to liquid. All right. Okay, so this is the sketch. Okay, I think this one is much more simpler compared to the bottom, to this one, to this figure. Okay, this is the sketch that we're going to use when we are solving the problem of distillation column. Okay, so you have this column, okay, and you have a feed. So usually the molar flow rate we level as F. So the mole fraction of A, okay, we level as a SF. Okay, so you have this distillate, okay, D in the mole per hour is actually the product coming out from the top part of the column, and this XD. So the one that going back to the column is labeled as a L. Okay, so you need to get yourself familiar with this F, L, D, and W. All right. So if you do this overall material balance, it's simple, right? You know, you see this is the border. Okay, the dashed line is the border for the overall material balance inside the distillation column. So simple, F is equal to D plus W. Okay, in is equal to out. And when you do the component balance on A, okay, it's also simple. You just multiply it with the mole fraction of A. Okay. All right, so this all is in a liquid form. Okay, either coming from the top or bottom is in a liquid form. All right, so tak ada apa kat sini. All right. Okay, now we go to the next slide. All right, yeah. So at the end of this class, okay, after we discuss all these things, okay, actually the objective is that we want to. Oh, saya tak termasuk lagi soalan. Okay, so the objective of this class for today is that we want to determine first, okay, the number of tray, N, okay, and also the location of feed tray. All right. And also we want to perform a simple distillation, as a simple mass balance. For example, a given to you the information and you want to find what is the value of D, molar flow rate, what is the value of W. Okay, so in order for you, okay, in example 11.4-1 here, okay, in order for you to determine this N and the location of feed tray, okay, you need to have at least 3 equation. Okay, 3 equation that will ada orang on mic ke? Is there any problem? 26. Okay. All right, you need to have at least 3 equation. Okay, because these 3 equation will help you to plot this straight line. Okay, so maybe I should mention here, okay, the first one is the enriching line, which coming from the enriching equation. The bottom part is a stripping line, okay, which coming from a stripping equation. And also you need to have this Q line. Okay, once you have these 3 lines from 3 different equations, only that you can calculate for the number of stages and the location of your feed tray. All right, so if you recall, okay, this is actually graph yang kamu dah plot sebelum ni. all right, which is the Y versus X. If you still remember that you are drawing a 45-degree line here, right? This is just a 45-degree line. Okay, so this curve is actually corresponding to your vapor liquid equilibrium curve. So that's why in the first class, I was mentioning to you that this vapor liquid equilibrium curve is very important, because this is the curve that we're going to use to determine, to solve our problem later. Okay, so in the first class, you have discussed on the Rod's law, on how actually you want to get the value of the Y and X, and how to plot this graph from the Rod's law. Okay, if the data of the vapor pressure is given. All right, so this is the objective. So now we go back on how actually, okay, the equation or the line of the enriching, and this one is stripping, and this one is Q is derived. Okay, so this slide is only a simple version. Okay, the more detailed one you can refer to the book. All right, so this is the equation for enriching line inside the box here. Okay, this is the equation for stripping line. And this one is the equation for Q line. Okay, so right now, in order for you to look up, okay, at this, you want to develop this enriching line, how actually this equation is developed. Okay, first you need to focus on the top part of the distillation column. So you can see here there is a dashed line here, means that this is the boundary that you're gonna make your overall material balance and your component balance. So you can see here, okay, you have a feed coming from the center of the column, okay, and here you have the Vn plus 1, okay, vapor phase coming into the border of dash line, and then you have the Ln coming out, okay, the liquid coming out from the borderline, and then you have the D, all right, the D here, the distillate product. So inside this dash line, okay, when you write down your overall material balance, is very clear, okay, whatever goes in is equal to whatever goes out. So Vn plus 1 is equal to Ln plus D, okay, in is equal to out. And for the components balance, what you're going to do is you just multiply it with the mole fraction of the A respectively. Okay, so V in vapor, so multiply by the mole fraction in vapor. So Ln and D okay. Ln and D is in liquid phase, means that you need to multiply by the Sn and Sd respectively. Okay, all right, so this is the okay, this is the first equation. Okay, now if you rearrange this equation, okay, you just bring Vn plus 1, okay, bring Vn plus 1 to the right hand side. Eventually, you will get this kind of equation. Yn plus 1 is equal to this right hand side. Okay, all right, so it's stated, okay, it's stated actually for a continuous distillation column, okay, there is two things that you need to know, okay, means here that Vn plus 1 is equal to Ln plus D, and the second thing is that the Ln over Vn plus 1 is equal to R over R plus 1. So if you refer to the book, R here is what we call as a reflux ratio. Reflux ratio means that here, okay, how much that you send back over the how much that you take out here, okay. So how much of the liquid that you send back to the column, which is the L, okay. So that's why R here is equal to L over D, And since we assume here that L is equal to Ln, so R is also equal to Ln over D. Okay, reflux ratio, the definition of reflux ratio is how much that you send back to the column over the how much that you take out from the column. Join class. All right, so yeah, okay. It's explained inside the book, okay. For the continuous rectification column, okay, Vn plus 1 is equal to Ln plus D. Okay, this one is actually coming from here. Okay, mana tadi? Vn plus 1. Okay, Vn plus 1 is coming from here. Vn plus 1, okay, the vapor coming in is equal to the liquid coming out. All right, so so from this equation, okay, we want to change this equation to this equation, okay. So you know that the Ln over Vn plus 1 is equal to R over R plus 1. So you just simply change this one into this one, okay. So for this part, okay, for this part, you need to use the correlation from here. Okay, so you know that Vn plus 1 is equal to Ln plus D. So if you divide this equation with Vn plus 1, it will become what? 1 is equal to Ln plus Vn plus 1 plus D over Vn plus 1. All right. And then so you know that the D here, okay, D over Vn plus 1 is equal to 1 minus Ln Vn plus 1. Okay, so what you're going to do is that you're going to replace this D with D over Vn plus 1. Okay, replace it with the 1 minus Ln over Vn plus 1. All right, so you know that this one Ln over Vn plus 1, okay, is actually equal to what? Ln over Vn plus 1 is equal to so Ln over, sorry, Ln, okay, semula saya tak cukup ni lah. Alright, so kita buat semula. Alright, so right now your Yn plus 1 is right now equal to R over R plus 1 Xn, okay, plus one minus Ln Vn plus 1 Xd. Alright, so you know that the Ln over Vn plus 1 is equal to R over R plus 1. Okay, so this term, this whole term is that U is equal to 1 minus R plus 1, right? So this one is 1 over 1. So if you make an arrangement, okay, eventually you will get is actually equal to 1 over R plus 1. So this whole thing you multiply by the SD, okay. So that's why from this equation it changed into this dxd over Vm plus 1 is eventually will change into the xd over R plus 1. So if you notice that this is actually a straight line, okay, y is equal to mx plus c. Okay, so this is the what we call as a enriching line. Okay, ym plus 1 is equal to R. Kejap ya kelas. Kejap. Okay, apa ya tadi? Alright, so you can see here, okay, the slope is corresponding to R over R plus 1. Okay, this is the X and the C, the cross section at the y-axis, the XD over R plus 1. So you know that the is XD, okay, this XD here refer to the mole fraction coming out from the distilled product. Okay, so R is the reflux ratio. Usually the value of R is given, okay, for the system. And then you have the X and Y here. Okay, so this is the equation for enriching line. All right. So now, okay, if you look up here, okay, if you get all the value by right with the, you can plot a straight line which is corresponding to the, you can plot a straight line corresponding to this enriching line, okay, and usually it is located at the top part of the VLE. Okay, if you have this vapor liquid equilibrium, okay, so usually your enriching line will situated at the top part somewhere here. All right, and then we go to the second part. Okay, so here is the equation for stripping line. Okay, this inside the box. So it's just a bit simpler compared to enriching line. Okay, so to develop this equation, okay, you need to refer to this borderline. Okay, here is the borderline, the dashed line here refer to a border for the material balance and the components balance to be carried out. Okay, so you can see here whatever Vm plus 1, okay, whatever out is equal to whatever into the system. Okay, so basically Vm plus 1 plus W, alright, so basically Vm plus 1 plus W is equal to Lm. So that's why Vm plus 1 is actually Lm minus W. So this is the components balance, just multiply it with the mole fraction respectively. And you make the arrangement, okay, bring this Vm plus 1 to the right hand side, and you will get also a straight line of the stripping line, which is y is equal to mx plus c. All right. Okay, so we assume that it's an equimolar flow, so you know that the Lm is equal to Ln. So maksudnya sekarang ni the mole fraction ataupun yang masuk sepanjang-panjang tray ni adalah sama. Okay, kita assume, to make it simplify, we assume it constant, even though by right in reality, of course, that the molar flow rate is going to be fluctuate between one peak to each other. Okay, so if you plot this stripping line, okay, on the vapor liquid equilibrium, okay, usually if your calculation is everything is right, okay, your stripping line will be located at the bottom part of the graph. Okay, so eventually, okay, you will get something like this after this. All right, you can see here, okay, you have the enriching line and you will have the stripping line. Okay, So that's why drawing a 45-degree line inside this graph is important, okay? Because the SD will touch at the 45-degree line, and you will get your enriching line, and your SW will touch on the 45-degree line, and you will get your stripping line. All right, so how to plot that kind of this line, okay, we will discuss later. Okay. All right, so the next thing, okay, this one is a bit complicated, okay, because you need to recall all the understanding on your knowledge on your thermodynamic before, okay, because in order for us to solve this problem, okay, we need to have another line, okay, which is what we call as a Q line. All right. So this is definition of the Q line, okay? The heat needed to vaporize 1 mole of feed at entering condition is equal to molar latent heat of evaporation of feed. So you know you have this latent heat of vaporization. Okay, it means that the heat needed to change 1 mole of molecule, okay, 1 mole of components from its liquid to vapor phase. Okay, all right. So you know that okay, this is the definition. Okay, so you know that the Q also can be rewrite, okay, as HV minus HF. Okay, so this HV minus HF means that is the energy required, okay, energy required to for 1 mole feed to change into the vapor. Okay, that's why HV minus HF. Okay, the energy required for 1 mole feed to change from feed to vapor. Okay, for HV minus HL, okay, it means that energy required for 1 mole of feed, okay, to change from liquid to vapor. Because if you understand about the concept of latent heat of vaporization, it means that there is no increment in pressure, no increment in temperature at that time, okay, because the heat supply is actually taken by the molecule to change its phase, okay, from liquid to vapor. So this is what we call as a latent heat of vaporization, and represented by the HV minus HL. Okay, so Q is actually the I repeat, okay, energy required for 1 mole feed to change into vapor over the energy required for 1 mole of feed to change its form from liquid to vapor phase. All right, and then this is equation number 1. Okay, let's say this one I label as equation number 1, and then we also have equation number 2. Okay, HV minus HF. All right, the energy required to change 1 mole of feed to vapor, okay, is equal to HV minus HL plus HL minus HF. Okay, because if the coming feed is in a liquid form, okay, so that the energy required to change the feed, okay, into the saturated liquid plus the change of energy, okay, required to change the liquid into the vapor. Okay, that means that is equal to HV minus HF. Okay, I hope you get it so far. Alright, then we go to this HL first. Okay, maksudnya sekarang ni bila mana the liquid phase coming into your feed, coming through your feed, okay, to the distillation column. Okay, so the feed, okay, need to change into the saturated vapor liquid first, right? The energy required, and after that, the saturated liquid will change into the vapor. That's why this term plus this term. Okay, so you know that for the change of 1 mole of feed, okay, in liquid to its saturated liquid form, is also can be represented by the CPL multiplied by the TB minus TF. Okay, let's say equation number 3 here. Okay, so the TB here refer to the boiling point of feed. Okay, what is the boiling point of your feed? Okay, so you know that usually the coming feed is in mixture A plus B. Okay, so you need to refer to the table lah. What is the boiling point? Okay, you cannot simply, for example, here the ethanol is 65 degrees Celsius. Okay, B is the water at 100 degree Celsius. So your component here, okay, your mixture here consists of 0.45A and 0.55B. So here the TB, the boiling point of feed is corresponding of the mixture 0.45 apa saya sebut tadi? Ethanol lah. Okay, 0.5 ethanol plus 0.55 water. Okay, so means that the temperature, okay, the T boiling point must be somewhere between 65 degrees Celsius to 100 degrees Celsius. Okay, that's the boiling point of feed. Okay, all right, and then you have TF. Okay, TF is the inlet feed temperature. Okay, so what is the inlet feed temperature of your system? Alright, so CPL here is the heat capacity of the liquid. Okay, yang masuk dalam kolom tu. Okay, you have F, right? So you need to know what is the CPL. Usually they coming in a liquid form. Okay, so the CPL. So CP here is also referred to the CP of the mixture A and B. And TB here is also referred to the boiling point of mixture A and B. Okay, so right now, right now you insert equation 3, okay, because we have the correlation HL minus FH is equal to CPL, okay, here. Why don't you insert 3 into 2, okay, masukkan, and all right, so let's say, let's rewrite again. Okay, so it become what is this? HV minus HF is equal to HV minus HL plus CPL TB minus TF. Okay, so let's say that this one is equation number 4. This one is equation number 4. Ish. Alright, so right now, after we get this new HV minus HF, okay, so right now insert 4 into 1. Alright, insert 4 into 1. So basically right now your Q is HV minus HL plus CPL TB minus TF over HV minus HL. Okay, B minus L, which is equation 5, which is corresponding to this one lah. Alright, so let's say this is equation 5. Alright, so here you can see here that from this equation, okay, we can eliminate the HF, because usually we have the data for the H vapor, H liquid, and we also have the data of the CPL and TB. TF is also, we know, right, the feed temperature. Alright, so this is the equation to represent the Q. Okay, tak habis lagi. This is not a straight line. Okay, so this Q, okay, usually if you're plotting the Q line, okay, inside this vapor liquid equilibrium, okay, if your feed, okay, enter as a vapor at the dew point, okay, so if your feed enter at its boiling point, then your Q is simply become equal to 1. So no need for you to susah payah nak plot a graph of Q line. Okay, you just make a straight line here. Okay, straight line here. Okay, so if your feed enter as a vapor at dew point, your Q is become a 0. Tapi but this case is quite jarang lah. Okay, biasanya tak ada lah feed tu masuk dalam bentuk vapor. Biasanya feed akan masuk dalam bentuk liquid, and we need to supply the heat inside the column. Okay, but in case that you encounter a situation whereby that the feed enter as a vapor, then you just simply make a straight line. Q is equal to 0. Okay, so the cold liquid feed, okay, Q is bigger than 0. Okay, for superheated vapor, Q is less than 0. Okay, so biasanya kes yang kedua ni pun jarang lah. Alright, so biasanya for a feed which is a part liquid, part vapor, okay, so Q is fall between this range. Okay, Q is bigger than 0 and Q is less than 1. Okay, so usually you have your enriching line here, stripping line here, and also another one is this Q line. This Q line is important for us to determine the location of the feed tray, because if you have this enriching and stripping line, eventually you already can calculate the number of stages, but we need to have this Q line to determine the location of your feed tray. Okay, kelas, saya kena stop dulu 5 minit boleh? Sekejap 5 minit. I know it's quite kita stop dulu, kita sambung dalam pukul 10.05, pukul 11 lah. Okay. Okay, class. Sorry for abrupt rest tadi. Okay, I have something to settle. Okay, so I know it's quite hanging, but just continue. Okay, with this developing of a Q line equation here. So right now we stop with equation 5 here, right? So you can see here this is the Q line whereby you can eliminate the HF. Okay, so you can have the HV, HL, CPL, TB, and TF. So this is the location of your Q line, okay, inside the vapor liquid equilibrium curve. All right, so now we go to the next part. Okay, so if you look out into okay, this equation is easy if you refer to a figure figure 11.4-6, okay, inside the book, because that sketch will make you understand about this equation. Okay, Lm is equal to Ln plus Qf. Okay, so Q here, okay, instead of the definition that we have discussed before, okay, the Q, this is the definition of Q, right? The heat needed over a molar length and everything. So this Q, if you look up into the inside the book, it also can be defined as a number of moles. If you read inside it, saturated liquid produced on the feed plate by each mole of feed added to the tower. Okay, so if you look into the figure 11.4-6, that will give you this Lm. So actually this Lm is the liquid, okay, a liquid entering the stripping, leaving the stripping border. Okay, so this Ln is actually the molar flow rate inside the enriching border. Okay, this one is from the coming from the enriching Ln. This one is the coming into the stripping. Alright, so sama juga. So whenever you see this M, okay, usually M is referred to the flow rate, okay, either L or M inside the stripping part. Okay, so you see the N here, okay, biasanya N here refer to the any molar flow rate, either is V or L in the enriching part. Okay, so if you do the this one is overall balance, this one is component balance. Okay, this one is components balance. Okay, so you just multiply. Okay, Vn plus Y is equal to ln(s) dsd. Okay, this one is for enriching, and this one for stripping line. So if you subtract these two, all right, Vm minus Vn, okay, you will get this equation. Okay, so okay, so how actually this equation will change into this? All right, so you know that from here, okay, I think anyone you try lah buat sendiri ya, okay, but you can see here, for example, Vm minus Vn here, okay, Vn minus Vn is equal to Q minus 1F, okay, so this one you replace by the Q minus 1F, for example, multiply by Y, and then you know that the Lm minus Ln here is equal to Qf, okay, and then this one, okay, you recall that, if you recall the first one that we have discussed before, that FSF is equal to DSD plus WSW. Okay, so this one you put it inside here. Okay, so after you make some arrangement, okay, there is a thing that can cancel out everything. Okay, so basically you will get this line. Okay, you substitute and make that arrangement. Okay, you will get this straight line to represent the Q line. So if you can see here, this Y is equal to Mx plus C. Okay, so your M here slope is equal to Q over Q minus 1. All right, so Miss here, in order for you to plot a Q line, okay, after you calculate the Q from this equation 5 here, okay, let's say you first need to calculate the value of Q. Okay, so you tengoklah what is the information given. If the question already give you all this information, for example, HV, HF, and HL, so you can directly calculate for a Q from the first equation. But if the information of HF is not given, but instead of that, it given to you the information of the CPL, TB, and TF, then you can calculate Q for the by using the equation number 5 here. Alright, so once you calculate the value of Q, okay, you can actually calculate the slope of the Q line. And okay, later on we will see how we're gonna plot a Q line, okay, by using the value of slope that you get. Okay, all right, so once another important things, okay, inside the book it stated that the intersection of the Q line equation, okay, the intersection of the Q line equation with the 45-degree line is y. The intersection of Q line equation with 45-degree line is y equal to x equal to sf. Okay, because in order for you to plot the Q line later, okay, you need this information. Okay, sf, which is eventually equal to x equal to y, and you can get the slope, and so that you can get the Q line. Okay. Just now we have discussed on developing an equation, three important equation, so that we will obtain to get three line in order for us to solve a problem in calculating the number of stages required in distillation column. All right, so usually, okay, the first step, usually when you want to solve a problem of the calculating the number of stages, first you need to have the equilibrium data between mole fraction of y and x, okay. Alright, so usually the first thing is that we try to solve for an enriching line and draw an enriching line. Okay, this one is corresponding for enriching line. Okay, and then it's usually start with the XD. So usually you know the mole fraction of XD. XD is the one coming from the top, okay, from the distillate. Okay, just put it into the 40-degree line and make a straight line of the enriching line. Okay, and can draw the Q line. Because usually the second step is that we draw a Q line. Okay, Q line, and this one is the first step, enriching line. And then the second step, okay, usually for the stripping line, okay, the third line here, kita biasanya tak calculate, okay, we not calculate because the stripping line is actually a line, okay, between the SW at 45 degrees Celsius, it's a 45 degree line, okay, to the intercept here. Okay, you have the intercept between the enriching line and the Q line. Okay, so the intercept here, you bring it to the 45-degree line, and that will become your stripping line. Okay, so how you determine the number of stages required? Okay, so it starts from here lah, from SD. Okay, so you have 1, 2, 3, and 4. So if you can see the SW is here, so approximately in this case, okay, your N is about maybe around 3.8 trays. Alright, so where is your feed tray, okay, feed plate is, you can need to see here, okay, dekat bahagian ni, so approximately at the feed plate number 2. Okay. Dekat sini, okay, Q line here, feed number 2. Okay, I think why don't you just take a rest for a while, okay, maybe 5 minutes. Okay, 5 minutes, okay. Tak apa, kita rest dulu 5 minutes sebelum kita buat example 11.4-1. So sementara tu, mana yang rajin boleh baca dulu soalan, and please prepare the graph paper. Okay, tak kisahlah nak graph paper manual ke, guna Excel ke, tak kisah mana-mana. Janji you need to plot all these things. Okay, so nanti kita sambung dalam 11.17 macam tu.
Doktor, mic doktor tengah mute.
Dah saya cakap seorang lah tadi. Alright, so it's okay. Sambung je lah, alright. So right now your SD is 0.95. And then at bottom, okay, W we label as W. And then we have SW, okay, as is 0.1 E. Alright, so I just label A so you know that this is a binary system. So by right, the remaining is the molecule B. Okay, so 0.45 A means that 0.55 B. Alright, so this is just a simple sketch on the system. Alright, so now let's move on to what as the information that has been given. Okay. Alright, so far clear untuk bahagian ni. Okay, so right now it's stated here that the reflux ratio is 4-1. Okay, so you know that the R is equal to 4. You can recall the definition is actually ln over D. Okay, how much you return over how much you take it out from the system. Okay, and then it's stated here the average heat capacity of the feed. Okay, average heat capacity, because you know that it is a mixture, so means that when you want to find the heat capacity value, okay, you can take off benzene or toluene, you need to find the average, okay, of the mixture. But right here it's easy, okay, you just straight away give you the value of Cp, okay, in liquid, which is 159 kilojoule per kilogram mole. Okay, all right. And then the average latent heat is 32.099 kilojoule per kilogram mole. Okay, so if you remember, what is the latent heat? Okay, latent heat evaporation is actually, okay, latent heat is actually an energy required to change 1 mole of the liquid from liquid phase, okay, to the vapor phase. So this value, when it's stated latent heat, if you, kalau kamu ingat lagi saya ada cakap kat atas tu, it's actually apa? HV minus, here HV minus HL, which is equal to 32.099 kilojoule per kilogram mole. Okay, the energy required, okay, to change 1 mole of your the system, okay, from liquid to vapor phase. That's a latent heat of, nama panjangnya latent heat of vaporization lah. Alright, so the equilibrium data is given, right? Previously, equilibrium data is given. If yang ada miss last class, okay, now we go to topic 1, part 1 here. Okay, this is the equilibrium data for the benzene and toluene system. Okay, if you refer at the inside the book, okay, table 11.1-1, okay, you need to, because you need to replot back this graph, okay, to solve for this problem. So refer to this table, and this is the one that you should get. Okay, this is the curve lah. Alright. Okay, the screen data is given. Now the question asks you, alright, the question asks you to calculate the kilogram mole per hour distillate. Okay, calculate distillate. Maksudnya the molar flow rate coming from the top, okay, in kilogram mole per hour. And then also apa dia? Kilogram mole per hour bottom. Okay, kalau bottom is that is W. Kilogram mole per hour. Alright, and then and also the number of theoretical stages needed. Okay, so we want to calculate the D, W, and N, and eventually if you solve for an N, actually you can also look up for where's the location of your feed tray. Okay, so you need to calculate for this three things. Alright, so I think the first one, okay, untuk D and W is easy. Alright. Okay, the first one, okay, overall mass balance. Okay, overall mass balance. Okay, F must be equal to D plus W. Right, so you know that 100 is equal to D plus W. And component mass balance. Alright, F as F. D as D plus W as W. So you have 100, 0.45 is equal to D 0.95 plus 100 minus D 0.1. I think this one's a very simple mass balance. Okay, you no need to make a revision on your CPV one. Okay, you know this is the first equation, the second equation, then eventually we can solve for D. So D is 41.2 kilogram mole per hour and W is 58.8 kilogram per hour. Okay, sorry, saya pergi laju sikit because I think this one is just a simple mass balance. Okay, on how you on the distillation column. Okay, now you have done with D and W. Okay, so right now we want to focus on how to calculate the number of theoretical stages. Okay, so in order for you to calculate, okay, for a number of theoretical stages, okay, so the first one is that you need to plot an equilibrium line. Okay, how you're going to plot it is that by looking at the table 11.1-1. Okay, so if you look at the table 11.1-1 inside the book, okay, so this 11.1-1, okay, you focus on the last two column. Okay, last two column, okay, there is a mole fraction of benzene toluene system, okay, at XA and YA. Okay, so right now boleh plot tak, and then plot tu guna Excel je lah supaya cepat sikit. Can you plot this first one, the first step here? Try plot sekejap.
Madam.
Okay, so the first step is, okay, you need to plot the equilibrium line, okay. And then the second step is that enriching operating line. You need to plot the enriching operating line here. All right, so you recall the equation yn plus 1 is equal to r plus 1 Sn plus Sd over r plus 1. Okay, so you know that the r value is given to you is 4, right? R value is 4, and then Sd, you also know what's the Sd. Sd is 0.95. Okay, so you can solve for this straight line equation. Eventually you will get that yn plus 1, okay, solve sendiri ya nanti, 0.8 Sn plus 0.190. Okay, because the value of Sd and R is known. Okay, so right now you need to draw the enriching line, because right now you have the straight line equation. So what you're going to do is just you pick up any value, okay. For example, that you have x and y. Okay, so in order for you to plot a straight line, you just only need 2 points. Okay, for example, if you get the x is equal to 0 and then y is equal to 0.19. So at 0, dekat graf kamu tu, okay, x at 0, y 0.19. And then just pick up any value, okay, any random value. X is 0.95, for example. Okay, and then what is your y value? It must be somewhere around here lah. Alright. Okay, sorry, this graph. Okay. Okay, so just plot a straight line. Okay, dekat bahagian atas ni. Alright. Okay, good so far?
Okay, Doktor.
Okay, so next step is we need to draw a Q line. Okay, let's say we go to the step number 3 here. Okay, Q line, okay. Okay, Q line. Now you refer to the book. Refer to the book of notes. Okay, just recall that the Q is HV minus HL. Okay, hope you just remember this equation. TB minus TF over HV minus HL. Okay, so you know that the HV over HL is a latent heat of evaporation, and it's actually the value is given, right? HV over HL is 32.099 kilojoule per kilogram mole. Okay, so same thing goes to CPL. Okay, so this value is given, CPL value is given, HV over HL is given. Okay, so right now your T feed is also given. Okay, your T feed is berapa tadi? Ada kan dia bagi? Alright. Okay, ada 327.6. Okay, so your T feed is given. So right now you need to find the TB. Alright, so to get the boiling point of feed, okay, because you know that is a mixture of the benzene and toluene. Alright, so right now you need to get TB at XA. So right now the mole fraction of X is 0.45. So to get this value of TB, you can refer to table 11.1-1, okay, the last two column. Okay, if you refer to the tables 11.1-1, the one that you used to plot the graph, okay, now look out at the value of XA. All right, so 0.45 is fall between the 0.581 and 0.411, right? So your value is 0.45 is here. So if you look out into the left hand side, not left hand side, I mean the first column, the 0.411 is corresponding to 36.82 Kelvin, and 0.581 corresponding to 363.2. Okay, so for you to get the TB value, okay, you need to find this X. Okay, make some extrapolation and eventually you will get the value of TB at SA is equal to 0.45. Okay, so once you get this value, okay, put the value inside this equation and you can get the value of Q, okay, more or less akan dapat lebih kurang sama lah, 1.195. Okay, so if you recall, okay, this is the equation, okay, for you to get the value of Q. And if you recall, okay, for the Q line equation, the M is equal to Q over Q minus 1, right? It's the one that you develop, you just flip your notes. Alright, so this Q, okay, means that 1.195 over 1. So okay, you will get this 6.12. Okay, so the slope for your Q line is 6.12. Okay, so how you gonna draw a Q line, okay, on your graph paper? Because right in here, so right now you already have 45-degree line. You already have a curved line of the vapor equilibrium, and you also have this enriching line here. Okay, so we want to draw this Q line, the slanting curve here. All right, so recall what I said before. Okay, the intersection of the Q line equation with 45-degree line is Y is equal to S is equal to SF. Okay, so by using this information, okay, we can draw our Q line. Okay, so you have, you know, that Y is equal to X is equal to SF on the 45-degree line. So 6.12. Okay, so your SF is 0.45. Okay, minus Y1. Y is just Y. Okay, 0.45 minus X. Okay, so you pick up any value of X that seems relevant on your graph paper. Okay, for example, let's X equal to, I don't know, maybe 0.5. Okay, so you will get the Y, and let S is equal to 0.55 maybe. You see Y is equal to what? Okay, so if you have these two point, okay, you will get the third line here. Okay, Q line here. Okay, this one Q line. Okay, dapat tak slanting curve macam tu? Should we try buat? Okay, girls, so far. Okay, you have this 45-degree line, curve line, enriching line, and the Q line right now. So I think the stripping line is easy because, as I said before, that you no need for you to calculate for a stripping line. How you draw your stripping line here is okay, you get the value of SW, right? Your SW is 0.1 and put it at your 45-degree line here. Okay, just drag the line into the intercept, okay, between the enriching line and the Q line, and that will give you the stripping line, the line of your stripping line. Okay, so there's no need for you to calculate for equation. Okay, just drag from SW at 45-degree line to the intercept between the Q line and enriching line. So by right sekarang ni your graph dah kena ada rupa-rupa macam ni lah. Okay. Okay. Okay, so last one we can calculate the number of tray from XD. Okay, so tray number 1, 2, 3, 4. Okay, I think you clear it. I think you clear. Okay, so approximately dalam 7.8 stages, or dalam buku ni dia kata starting at the XD. Okay, the theoretical is 7.6 steps. Okay, so you have 7.n is equal to 7.6 steps, and usually dia kata this step is actually including the reboiler, because for the continuous distillation, okay, you have the reboiler at the bottom part. So because of this step is actually including the reboiler, so your actual n is 7.6 minus 1. 1 here is reboiler, so the total stages is actually 6.6. Theoretical 3. Theoretical tray, and the feed is introduced on tray 5 from the top. Okay, so you can see here, you make a for how to say the perpendicular line here. Okay, is about at the your tray feed is about at 45. Tray number 5. Okay. Any questions so far? I think that we should stop here. It's time lah kita masuk untuk reflux ratio. So any questions so far? No?
No, doctor.
All right, yeah. So I think it's quite heavy today, okay, not like previous class on introduction to distillation column, okay. However, okay, this one of the most important part for the design in distillation column, which is the determination of N, okay. So I hope that you can go through it once again, okay, on how to develop the equation, the concept, and the example. Okay, so for the next class, instead of maybe I should finish first, okay, the syllabus, which is on the minimum reflux ratio and the the total reflux, minimum reflux, and the optimum reflux. And then only that we can maybe do some tutorials, okay, to strengthen your understanding about this topic. Okay, so okay, I see you on Friday. Okay, I see you on Friday at 10 a.m. All right, so next week, most probably we're gonna have only one synchronous class. Okay, so basically maybe untuk kelas yang pertama minggu depan saya akan buat recorded video. Okay, just watch the video and give you some comments. Okay, or you can just WhatsApp me if you doesn't have if you don't understand, and then maybe I only meet you at Friday. Okay, for the tutorial class. All right, so if you doesn't have any question, I think we should stop our class today. All right, so thank you so much for your attendance and your attention. So Assalamualaikum. Thank you.
Waalaikumsalam.
Waalaikumsalam.
Okay, doktor.
Thank you, doktor.
All right.
Thank you so much, Doctor.
Thank you, doktor.
Madam.
Thank you, doktor.
Welcome.
Thank you, Doctor. Thank you, Doctor.
Welcome.
Thank you, Doctor.
Welcome.